Yeah, good morning. In this session, I would like to demonstrate the estimation of physical properties of a pure component. In fact, this can serve multiple purposes. If a component is already available in the database of a process simulator, we are interested in looking at certain properties of that compound, extract this information from the database. That could be one option. The second option is, for example, when you are simulating a process, you might come across with a component which might not be available or which might not be listed in a process simulator. Just because that particular component is not available, do you think you will not be able to simulate the process? So in such a case, ASPEN provides an option of estimating the necessary properties by giving minimum information like the molecular structure. So we will try to see both these options through ASPEN. Now let me first of all try to show you. Suppose if I am interested in looking at benzene, because the molecular structure is automatically obtained, it is available in the database. So if you want to retrieve the properties from the database of ASPEN regarding this particular component, you can go to NIST thermodynamic engine, click on this, select the component that you want, and then say evaluate. Yeah. Now you can see various properties tabulated in the database as far as this compound is concerned. This has a function of temperature. The parameters involved in that equation are already available. So once you note down these parameters, you will be in a position to calculate the thermal conductivity at any given temperature as far as this compound is concerned. Probably you can spend some time and look at, if you are interested, on some of the properties that are available. So this is one case. Now let me delete this compound, and I would like to now deal with a compound which is named like this. It is also a conventional compound. You don't expect this component to be present in the database because it's my name, right? In such a case, we will be able to define this as user defined. You can, if you want, you can give an alias name and go to the next. So if you know some of these properties, it might help you to predict the properties more accurately. By giving the molecular structure using the group contribution theory, we will be able to for a pure component. Even if I don't know, still I wanted to go ahead, and I am checking this option for the time being. We will see the first option slightly later. So I am going to define the molecule by its connectivity. Click on this. Now, before you want to run this problem, you need to draw the structure on a piece of paper, including the type of bonds between these atoms, and ignoring the hydrogen atoms, try to label them with some serial number. Label all the other atoms excluding hydrogen with, as per your convenience, give some numbering. So it doesn't matter how this numbering is done. For example, I would have started with 1 instead of 5. But based on this numbering, now you try to define this structure to ASPEN. In this case, you can see that there are 5 atoms excluding hydrogens. 1, 2, 3 and 5 happen to be carbon. 4 is oxygen, and you can see that all the atoms available in this example are single bonds. So let us try to define this information here. So atom number 1, as per my label, defined as carbon, and it is connected to atom number 2, which is also carbon. And of course, you saw that the components are, all the bonds here are single bonds. Now in the same way, atom 2, which is defined already as carbon, is connected to atom 3, which is also carbon, by again single bond. Then 2 is also connected to atom 5 as per the drawing, which happen to be again carbon by single bond. 1 is connected to 2, both happen to be carbon. 2 is connected to 3, both happen to be carbon. 2 is connected to 5, both happen to be carbon. Now we need to address this part, 3 to 4. So atom 3, which happen to be carbon, is connected to 4, which happen to be oxygen. All the bonds are, of course, single bonds. Now, like this, you should be in a position to define the molecular structure along with bonds. Once you do this, you can close this window. Again, you can say next. So you are trying to estimate using ASPEN property estimation system. Say finish. Okay. Now, by default, when you open ASPEN, you will be doing property analysis, but we are now interested in calculating or estimating the properties. So check whether you have this tab selected. If not, you need to highlight this, estimate all missing parameters, then say next. Okay. So run property estimation. Okay. The results of this property estimation. Now these are the properties we were able to calculate by giving minimum information like the molecular structure. You can check up whether the molecular weight, which we have not provided, has been computed properly or not. Similarly, normal boiling point, critical temperature, critical pressure, critical volume, critical compressibility factor, ideal gas heat capacity at 3 different temperatures, standard heat of formation, standard free energy of formation, vapor pressure at normal boiling point, 90% of the critical temperature, at critical temperature, eccentric factor, and so on. Now, in the same way, you should also be able to look at what estimated, the parameters involved in this equation are given here, and you can actually check up what is the natural form of the equation ASPEN is making use of. For example, normally we know Cp in the ideal gas phase is represented by an equation of the form Cpig by R is equal to A plus Bt plus Et square plus dt power minus 2. But you can see there are several constants involved in this equation. Probably you can go into help and see what is the actual equation ASPEN is making use. These are the two temperature limits. 280 is the minimum temperature, 1100 is the maximum temperature between which you can use this equation. And you will be having information about these constants from the equation. You can check it out. Similarly, vapor pressure, how is it going to be a function of temperature is the parameters involved in this PLXCINT, extended Antoine equation, they are available. So like this, you will be able to see some of the properties, if they are functions of temperature, they can also be estimated at any given temperature. Now, all this we were able to calculate based on simple molecular structure. Of course, you can see the methods used for estimating each of them. If you want, you can go into literature and observe what and how you will be in a position to estimate these. Similarly, even in the case of pure component properties, these are the default methods made use by ASPEN in estimating the necessary properties. Without having an idea about these property methods, don't try to change these defaults, right? So this is how you will be able to estimate the properties of any compound that might be available, that might not be available in the database. Now I would like to show you another example. For example, MTBE. You can go to internet and Google NIST chemistry webbook. Just click on this link and you will be able to search for the name of the compound in this, for example, MTBE. Search. Now you can see the chemical structure of particular compound is already available in this NIST database, chemistry webbook. So you will be able to, without specifying the molecular structure, you can import and use it for estimating the properties. For example, ASPEN can take the 2D mole file format. Just click on this. You will be able to get this 2D mole file. Once you have such information, Once again, I'll be able to make use of this in ASPEN to estimate the properties. I'll go back to the components, conventional, user defined, next. Now I'm selecting, instead of defining the molecule by its connectivity, I'm selecting draw or import edit structure. In fact, ASPEN also provides some kind of a user interface to draw the molecular structure. Maybe with little practice, you will be able to draw the chemical structure. But right now, I have already downloaded the chemical structure in format for this particular compound, MTBE. So let me check up where is it available in downloads. So this is the 2D mole format I'm opening. So this is the molecular structure of MTBE. So now you don't have to specifically atom to atom the type of bonds. All that information will be retrieved from the molecular structure that is already available. So you can close down this window and then next. Now the moment you have molecular structure, you will be able to evaluate the properties of the thermodynamic engine. Say evaluate now. Now you can see the properties are estimated for this particular compound by importing the molecular structure, right? You can check it out. So like this, you should be in a position to calculate the pure as well as some of the other results. So these are some of the options that are available if you are interested in calculating the properties of a pure component. If the component is available in the database, you will be able to. And if you can find the molecular structure in NIST chemistry webbook, you can directly import the 2D mole file and use it for estimating the properties. This could be one option. The other option is you can also define the molecule by its connectivity. Typically, when the components are shorter, it may be possible for you to define the molecular structure. But if it is a very lengthy compound involving a lot of atoms, it may seem to be slightly more cumbersome. But again, for doing such problems, though I may not be talking about this, you can define the structure and functional groups. You know, you have to identify the groups, how many times each group is appearing. So by giving even this type of information, you will be in a position to estimate the properties of any pure component. So with this, I would like to close down my session.